Hi everyone, welcome to this SWAPA 2021 workshop video on getting started in Bayesian statistics and psychology, a workshop using JASP. My name is Tom Falkenberry and I'm an associate professor at Tarleton State University in Stephenville, Texas. And I usually look forward to giving one of these workshops at SWAPA most years. Unfortunately, I couldn't be in attendance at SWAPA, and so we'll have to settle with a video this year. But I hope that this will actually give you a resource that you can go back and watch when you have questions later on. So the way these workshops usually go is I like to give you some of the basics of Bayesian inference, this thing that people have heard of before. I want to kind of explain what it all means and then give a really good concrete example as well as show you how to write it up. And then I always like to take questions from the audience, but unfortunately we can't do that this year because this is being recorded before the fact. But if you do have questions for me after this workshop, please do feel free to contact me, and you can see my website, and I'm also on Twitter right here on this title page, and I'll also tell you the slides for this workshop will be available, and I'll show you that in a second. So with that, let's get started and see what we can learn about Bayesian statistics. So my outline today is I want to really go through four things. The first thing that I want to do is address the burning question of what's the difference between what I'm used to doing, which is probably inference with p-values, versus this Bayes thing, these Bayes factors that I keep hearing about. What are they and how are they different? Is a Bayes factor just another number that replaces the p-value? The answer is no, it's more than that, and you'll see why in a second. And the second thing that I want to do is discuss some misconceptions about the notion of priors. A lot of people use the prior as the thing that is sort of the death knell for the Bayesian inference way of doing things. Well, I can't do that. I don't want to do this because you have to specify these priors. And it's really not all that bad. So I want to talk specifically about the difference between priors on models and priors on parameters. They're different types of things, and they each have their own role in the game of Bayesian inference. Then I want to make sure that we do a concrete example. I'm going to do an example of correlation today. That's one that is related to a lot of what you typically see in a lot of psychological and behavioral science papers. It's a simple example. Most everyone knows what a correlation is, and so it's a good way to get started in actually performing the Bayesian inference as well as reporting the results of the Bayesian inference. And to that end, I make sure at the end and I give you a reporting template. If you do a traditional test like a correlation test, you probably know from your examples in school, this is how I write it up, but what do you do with the Bayes factor? So I'm going to show you that. And then at the end, I'm going to point out some more resources that I think can take you further if you're interested in going down this road, and I really hope that you are. So as I mentioned before, these slides can be downloaded from my website. My apologies if that's a little bit hard to read, but it's just my name, tomfalkenberry.github.io/talks.html. And if you just go to the github.io site, there's actually a link on that page for my talks. And this will be available as a PDF. Okay. So with that, let's get started, and I want to frame our discussion today in terms of this example. So let's suppose that we are interested in the relationship between math anxiety and performance on some standardized assessment. Now, I'm interested in math cognition. Besides being a methodologist, I'm also a researcher in math cognition, so this is the kind of thing that I might be interested in looking at. We can design a study to figure out this relationship. It's a nice correlational design. Well, how does it work? How do we do these things? So you probably remember how the game of statistical inference works. Let's review that. So the first thing that we do is that we define hypotheses about some population parameter. Now in this case, it's a correlation. So we're going to define some hypotheses about this population correlation rho. Now if that looks like a P, that's just the way the Greek alphabet looks. It's actually a rho. It's the Greek letter for R, the typical symbol for correlation. So what are these two hypotheses? Well, we're going to make them very simple hypotheses. The null hypothesis is going to be the hypothesis that there is no correlation between math anxiety and performance. That is, as a number, rho is equal to 0. And then the alternative hypothesis is going to be that rho is not equal to 0. And that would mean that there is some non-zero relationship or correlation between math anxiety and performance. So essentially, we've got the game set up. We have two a priori hypotheses about this correlation between math anxiety and performance, and now we want to collect some data to see if we can figure out which of these two models is best, right? That's the game. So how does it work? Well, let's go from that step. Once we collect the data, the frequentist view, so this is probably the traditional way of doing things that you've been taught, is to compute something called a p-value. And all the p-value is, we think of it as this magical dowsing rod that allows us to assess significance. I mean, it just sounds kind of silly when you think about it that way. It's really nothing more than just a simple probability. It is the probability of observing that data that you have under the null hypothesis. This is a conditional probability. It says if the null is true, here's the probability of getting your data. Now, if your data is relatively unlikely to have occurred under the null hypothesis, then something's going to happen here. And specifically, we interpret it this way. If p is small, that is, it's a small number, that tells us that our data is rare under the null. It couldn't have happened. So what happens is we reject the null in favor of the alternative. Okay, so remember, it's that idea of to get a, quote, significant effect, you need to be able to reject the null hypothesis. And we do that, again, on the basis of this p-value. Now, that's pretty well gospel for most people attending this talk. You're probably familiar with that. If you're a student and you're not familiar with that, I might encourage you to just ignore this column, and let's consider another way of assessing how well our data fits these two competing models. That other way is the one I want to talk about today, and that's the Bayesian way. So how does it work? Well, instead of computing the p-value, we compute something different called a Bayes factor. Now, if you look at the mathematical form of this Bayes factor that's presented, it looks a lot like, a p-value plus another part. In fact, it's a fraction. Now, it's actually quite different. This is a different kind of probability when you get under the hood, but it's okay if you think about it in that way, that it's just a p-value divided by another p-value. Again, those of you who are Bayesians know that I'm absolutely speaking nonsense right now, but just hold on to that for a second. So let's look at this thing. This Bayes factor is a fraction that says I take the probability of the data under the null divided by the probability of the data under the alternative. It's almost like it's a relative p-value. It's the likelihood or the relative likelihood of observing my data under one hypothesis compared to the other. That's exactly what a Bayes factor is. And here's how we interpret the Bayes factor. If that Bayes factor, BF01, is bigger than 1, okay, then that means that the numerator of this fraction has to be the bigger number. So that means that the likelihood of the data under the null is bigger than the likelihood of the data under the alternative. In other words, the data are more likely under the null hypothesis. On the other hand, if this Bayes factor that we get is less than 1, that means the denominator has to be the bigger number. In that case, that would mean that the probability of the data under the alternative is greater than the likelihood under the null. So that would mean, again, that the data are more likely under the alternative. Now, this is kind of interesting, and I want to point this out in detail here on the next slide, but this is already, to me, a better state of affairs, because this little thing right here can directly tell you whether it's the alternative or the null that was more likely to have produced the data. You don't get that with this. You only get the likelihood of the data under the null, not the alternative at all. So let's really dig a little deeper into that and compare these two notions, this p-value versus this Bayes factor. So the point of this discussion is now to say, okay, some people will argue that, well, I'm not going to use Bayes factors because they're just a p-value in different form. If I do one thing, I'll get the same conclusion with the other. And that's actually not true, and it's even deeper than that. They are conceptually completely different things. Okay, let's dig into that. So what is a p-value? Well, from above, we saw that the p-value is just this probability. It's the probability of the data under the null. So what the p-value does, and this is actually its downfall, is that it only considers the fit of the null as a potential model for our data. It completely ignores the fit of the alternative. So it could be the case that the null is a bad fit, okay, low p-value. But it could also be the case that the alternative is a bad fit as well, and so you're simply trying to find the better of two really bad fits. Is that what we want to do? I don't think it is. So in this case, the p-value is quite limited, and of course we know this already, because that means that when we reject the null, this support, and notice I'm putting that in quotes, for the alternative is only ever indirect support. It's never direct support. It's just simply, well, the null doesn't work, so it must be the alternative that's the winner. That seems lacking. Okay, it seems lacking to me. But let's contrast that with the Bayes factor. The Bayes factor, yes, it's a number, but it's a fraction. It is a relative performance. It is telling you the relative adequacy of both models simultaneously as predictors of the data. So whereas the p-value only looks at the null and then bases all decisions that you would make on that number, the Bayes factor takes both models into consideration at the same time and measures this relative predictive adequacy. Okay. And as such, it doesn't care which model's best. It just tells you these data are more likely under this one or this one. It could be the null, it could be the alternative. In that way, it can directly index support for either of our models. So let's end this little part with a concrete example of how you would interpret a Bayes factor. Let's suppose that you get a Bayes factor of 8. And now I know what you're thinking, wait a minute, how do you compute these Bayes factors? Well, there's software out there that will do it very, very easily. So before we jump into that, we should probably look at how you actually interpret the numbers that you get. So let's again, suppose we have BF01 equals 8. So what this means then, by the definition above, is that the observed data are 8 times more likely under the null than the alternative. Why is it that? Well, it's all about this subscript that we have right here. If instead we had written BF10 equals 8, okay, then that would be the opposite. That would say that the observed data are 8 times more likely under the alternative than the null. So this subscript down here is directional, and that in that direction makes a difference. So you'll know from your software which of the two you're getting. It won't just be a naked number. You'll have either BF01 is 8, and that would be support for the null, or you'll have the other way, BF10 is 8, and that would be support for the alternative. And of course, it doesn't always have to be 8. It could be anything. So what exactly, what values are we looking for? After all, with p-values, we're calibrated to think, okay, if it's less than 0.05, maybe I'm getting somewhere. Maybe if it's even smaller, that's even better, right? But certainly we know how to act with p-values. We might not know how to act with Bayes factors. So to that end, there have been several recommendations passed down over the last more than 50 years, probably 70-ish years at this point, and they've come from various people. The ones that I'm going to present here are due to Harold Jeffreys, who was one of the big developers of the Bayesian techniques that we use in the psychological sciences today, even though he was a physicist. So Jeffreys in 1961 proposed the following scale. And that is, if you have a Bayes factor between 1 and 3, that we would call that anecdotal evidence. 3 up to 10 we might call moderate evidence. 10 to 30 is strong. You can see it just keeps getting bigger. So in the end, with Bayes factors, bigger is better. If you get a Bayes factor of 1, that's like the baseline, right? That says that both models are equally likely. The probability of the data under one is equal to the probability of the data under the other. So you want things 1 or bigger, and the bigger the better, the more evidence that you are getting for one model over the other. Now, I do want to caution you that these are only guidelines. My recommendation is not to get hung up on the label of the evidence, but rather report the number and let the context declare or help you to declare which kind of what strength of evidence you have. So just report the Bayes factor, say what it means, and let the science debate go from there. So with that, let's get into a little bit of the mechanism. How does Bayes work? How do we get these Bayes factors? So I'm not going to get too technical. Really, just like any statistical inference, if you want to do things by hand, it does take a bit of mathematical work. And that's not my point today. My point today is to give you a conceptual overview of Bayesian inference. Well, how it works is really based on something you may already know a little bit about. At some point, you may have heard about Bayes' theorem. And Bayes' theorem is this thing in the yellow box here. And in the context of models with data, this is how it works. Under Bayes' theorem, we can find the probability of a model or hypothesis H after seeing data. So this is called the posterior probability, by taking the prior probability for that model and multiplying by an updating factor. This updating factor is basically what's the probability that you would have seen your data under the model compared to the probability of the data under all possible models. So this is the form of Bayes' theorem. There's not really much that we can do with that today, but it does give us a nice little mnemonic here. For Bayes' theorem, it's always posterior equals prior times updating factor. And that's really a nice metaphor because science works this way. We take our prior belief in something and we collect data, and that updates our belief into a new belief, a posterior belief. So in a sense, Bayes' theorem is just a philosophical mathematical theorem. Okay, it's a mathematical theorem that matches philosophy. Okay. Now, I'm more interested in the case that we were considering earlier, and that's not when we have a single model like this. Let me get my thing going here. Come on. There we go. It's not for a single model, but rather when we have two models to compare. So what would Bayes' theorem say in that case? Well, for two models, we would simply divide the two posterior probabilities by each other. So say we're going to compare the null hypothesis H0 to the alternative hypothesis H1. Well, then our posterior odds, which is what this quotient would then be equal to the prior odds divided by this updating factor. And this updating factor is the Bayes factor. So this actually gives us another definition of the Bayes factor. Not only is the Bayes factor the relative predictive adequacy of the data under these two models, but it's also the factor by which my prior odds are updated after seeing data. Okay, so it's the Bayes factor is an updating factor. Let's see exactly how we'll get there in just a second. We're going to see how that works in just a minute. I know it seems like I'm jumping here. I'm stopping at a really crucial point, but I need to bring up something before I get into the next little piece, which will clarify what I mean by this statement here. And that is, what do I mean by prior things, prior odds, prior parameters, etc. So let's look a little bit more deeply into that. What do we mean by prior? Again, this is the thing that people tend to leverage as a criticism against Bayesian statistics. Well, there's actually two different types of priors that we might be talking about when we say the word prior. One is priors on models, okay, and the other is priors on the parameters within a given model. So let's discuss these a little bit and see what the difference is. Oops, that's not what I wanted at all. Here we go. So first, let's look at priors on models. So before observing the data, we might ask ourselves, what's the relative likelihood of these competing models? Okay, which one's more likely than the other before observing the data? Otherwise, what's otherwise known as a priori belief or relative a priori belief. So a common default for this is to just set them equally likely. That is, that before seeing the data, let's just assume that the probability or the prior probability of the null hypothesis is the same as the prior probability of the alternative, and those are both equal to 1/2. We would call this 1-to-1 prior odds. Now notice they have to be equal to 1/2 because the prior model probabilities must add to 1. You have to have two things that add to 100% or 1. So in this case, that certainly does match. Now, when we do this, okay, remember Bayes' theorem says, now after we observe the data, we update these prior model probabilities, and we can actually then compute the posterior belief in one of those models by applying the Bayes factor. Now, it's not trivial why this is the case, but if you'll take it for just take it for granted right now, what this tells me is that if I start with some prior model beliefs, and then I know the Bayes factor, that I can actually use that to directly compute the posterior probability of that specific model. And if you wanted the probability of H1 instead, then it would be no different. We would just switch some of the subscripts around. But an easier way to look at this theorem is if we assume these equal prior odds. Remember, that's a common default. We just say, let's assume they're a priori equally likely. Then you actually get a very simple expression for the posterior probability, and that's just the Bayes factor plus or over the Bayes factor plus 1. So we'll see some examples of this over the next few slides. So let's look at an example of this idea of the Bayes factor as an updating factor. So let's suppose that we, again, looking at these two models, H0 and H1, if you don't remember what those are, go back to the very beginning of the talk. Remember, the H0 is that there's no correlation between math anxiety and performance, and H1 is that there's some non-zero correlation. So before seeing the data, let's assume that those two models are equally likely. So if I plotted them in a little pie chart here, they might look like two halves of the circle. Half the pizza is, say, pepperoni, and the other is cheese. Now, we call these prior odds 1-to-1. Now, what do we do in science? Well, we start with this prior belief, I don't know, and then we collect some data. So let's just say that we observe the data, and we compute one of those Bayes factors, and we actually find out that the Bayes factor for the null over the alternative is equal to 9. So what does that do? Well, what that does is update the relative prior belief into now a relative posterior belief, and it looks exactly like this. If you look at the posterior probability of the null divided by compared to the posterior probability of the alternative, these are now in 9-to-1 odds. Now you may be wondering, where does 9-to-1 come from? Well, remember, the Bayes factor is the factor by which you multiply these odds. So if I've got 1-to-1 prior and I multiply by the Bayes factor, that becomes 9-to-1. And as posterior probabilities, that equates to 9/10 of the circle, or 90%, is now red, and 1/10 or 10% is white. So that's a visual of what's going on with the Bayes factor. So here in this picture, we have the two ways you can interpret a Bayes factor looking at us. You've got the updating factor idea. That is, it's the factor by which we update our prior odds. So we've gone from 1-to-1 to 9-to-1 odds. And then it's also the relative adequacy of the models to have predicted the data. The data are 9 times more likely to have predicted the data under the null hypothesis than the alternative hypothesis. Let me say that one more time in case I kind of messed it up. The null is 9 times more likely to have given us these data than the alternative. Okay. So that's what we mean by model odds. And if you want to see how to work out that posterior probability of 9/10, you can just use that little formula that I mentioned, and I'll show you another example just a little later in the talk. You take the Bayes factor and you divide by the Bayes factor plus 1. That gives you 9 over 9 plus 1, which is 9/10. Okay. So that's what we mean by prior odds, prior model odds. The other way that the word prior comes into this discussion is the priors on parameters within a given model. And this is a different kind of prior. So let's kind of take a step aside and see what this is all about. So first of all, let's remember our model definitions. Remember that the null is that the correlation coefficient is 0, rho equals 0. And the alternative is that it's not equal to 0. Now the null has a very specific hypothesis. I know exactly what that means. It means that rho equals 0. There's like no other way that you can conceptualize that. But the alternative is a little bit fuzzy. The alternative is that it's not equal to 0. But what exactly do we mean here? Because there's a whole infinite set of values that could be not equal to 0. So are the ones at the end, like 1 and -1, more likely than the ones in the middle, or less likely, or are they all equally likely? We really don't know. We haven't totally specified what we mean by rho not equal to 0. So the prior is used to quantify this uncertainty. We quantify our uncertainty about that correlation by placing a distribution on the possible values of rho. This prior is really a prior probability distribution. So for example, let's suppose that we have no idea what to expect with our correlation. So in this case, just like above, when we looked at the prior model odds being 50-50 or 1-to-1, we might here believe that any value of rho is equally likely to occur. And so in that case, we would say that rho is uniformly distributed on -1-to-1. Why -1-to-1? Well, remember, correlations can only extend from -1-to-1. So we need to make sure that we're not putting any mass on impossible values of the correlation. So what does that look like? Well, it might look like this picture right here. The prior is simply a distribution that is flat, that extends from -1-to-1. So this means that before seeing any data, so hide all that over there, before seeing any data, this value of the correlation is equally likely to occur as this value, as this value, as this value. All of them are equally likely to occur. So that's a good default belief for the correlation coefficient. Now, of course, after we observe data, we can use Bayes' theorem to get a posterior distribution. And so if we observed a correlation out here, like close to 0.5 or something, then what that would do is take this red curve and it would peak it right here, okay? And it would kind of shift things around. The mathematics of what's going on is a little bit hard to describe, but if you, again, can just kind of believe what I'm telling you, this is what happens when you observe data. You shift this distribution, and then when you multiply it by the likelihood function, it turns into this nice little peaked distribution. Now, here's one of the interesting things. I'm getting a little bit ahead of myself, but I'm going to show you something on JASP in a minute that is going to reflect what we're talking about. If you were to take these two curves, the prior on the left and the posterior on the right, and you were to overlay them, so I'm going to move this over to here. Oops, I'll try to get it all lined up. Then there's actually a very neat relationship that happens, and here's that relationship. We're going to look at the value of rho equals 0, okay, so this correlation right here, the null hypothesis correlation, under both the prior and the posterior. Okay. And what we will notice is that after collecting data, the likelihood of this value of the correlation, the likelihood of 0 in the prior, decreases, so it goes down to here, quite a bit. And the factor by which we decrease the probability of rho equals 0 after seeing data is absolutely the Bayes factor. That Bayes factor is the factor by which the belief that rho equals 0 decreases. Okay. Changes, really, but in this case it decreases, right? So what that means is we're going to get BF01, I'm going to make up a number here, maybe it's like 1/10, okay? So we multiply by 1/10, that means that BF10 is just the reciprocal of that, is just 10. That means that the Bayes factor for the alternative is 10. The data are 10 times more likely to have occurred under the alternative than they are the null. Now, the reason I point this out is because you're going to see a graph in JASP, and what that graph is reflecting is this little fact right here, that we can actually compute the Bayes factor by considering the motion of rho equals 0 from prior to posterior. And that fact has a special name. It's called the Savage-Dickey density ratio. And so you may see that referred to in some papers. And I want you to know what that is. So that's what that's referring to. Yeah, that's enough of that. So we'll see this here in just a moment. So let's get back to our example. So let's suppose we have some data. What do we do with it? I don't know, suppose we tested 65 participants. Remember, what are we looking for? We're looking for the correlation between math anxiety and some math performance. So let's say that we tested 65 people and we observed a correlation of 0.37, a Pearson's R of 0.37. So I want to do a Bayesian analysis of this. To do that, I'm going to use JASP, which is a nice free software package that I'm going to introduce you to in a second. And specifically, we're going to use something called the Summary Statistics module in JASP. So first of all, if you don't have JASP, it's really easy to get. You just simply go to jasp-stats.org and you can download it. And when you click on download, you will see that you can easily get a Windows version, a Mac OS version or Linux version. And in fact, some of the newer Chromebooks can install Linux now, and you can also run JASP in a browser via something called Roll App. And so there's some tutorials on YouTube about how to do that. Either way, whether you're a student or someone who teaches students, you should realize that JASP is absolutely accessible across a wide variety of platforms. And if I didn't mention this, it's absolutely free. It always has been and always will be. And that's, again, one of the great things about JASP. So I've, of course, already got JASP installed. So I'm going to open up my installation of JASP now. And so there it is. This is the, as of this video, JASP version 0.14.1 is the newest version. And it looks just like this. Now, the way JASP works, just to mention, is it works with what are called CSV files. So when you go to the open dialog, you're going to be looking for CSV. That's comma separated value. It will open SPSS files, those with a .sav extension, but it will not open XLS files. So if you're working with data in Excel, which a lot of us, of course, do, just be sure and save that as a CSV file. You just change the file type and it will work. But I'm not actually going to do that here because I have already calculated the correlation. It was 0.37. So if I have the summary data already, then I don't have to load any data into JASP. I can just open something called the summary statistics module. So that's what we're going to do here. To do that, we're going to open this little plus sign, and it's going to show us a bunch of extra modules. The one I want is the summary statistics module. When I do that, of course, it pops up a little extra module in the top. I'm going to click on that, and you'll see what I have available are a bunch of Bayesian tests. And I specifically want to do a Bayesian correlation. And so when I open this up, it's going to ask me to enter some things. Now, all I need are two pieces of information. I need the sample size, which I gave us as 65 just a second ago. And then I need the size of the correlation coefficient. So what was Pearson's R? And we said it was 0.37. And as soon as I hit tab out of that, you'll see immediately that I get a correlation table that gives me not only the two summary statistics that I just produced, but it also pops out a Bayes factor and a p-value. So everything immediately happens. It's almost like it's too quick. So we're going to interpret this Bayes factor in just a minute, but I want to show you some of the other things that we can choose. You can choose something called credible intervals. If you do that, it's just going to add it to the table. I'm going to keep my table clean right now, so I'm going to remove that. But I am going to choose the prior and posterior plots. And it takes just a second for that to pop up on the right, and it's a little big. So I'm going to move this to the left just to hide the input stuff. And I've just got my output. You'll see that what I have here is exactly one of those plots, just like I drew on the slide before. This is that prior to posterior updating. This is really kind of a nice plot because in this one plot, you get a lot of the very visual outputs that you get with Bayesian inference. What are they? Well, first of all, it shows us what our prior was. The prior was a flat or uniform curve going from -1 to 1. That's the dashed line. The posterior is peaked. It's going to be peaked around whatever the sample correlation was, which was 0.37. It shows us the 95% credible interval. So that's different from a confidence interval. This is a probability statement. This says there is a 95% probability that the correlation is between 0.134 and 0.554. That's pretty strong. That's not saying that 95% of the time I'm going to capture some unknown population parameter, which is what a confidence interval does. No, this is, there is a 95% likelihood that my parameter, my correlation is between those two values. Gives us the median of that distribution. Here's the Bayes factor. It says that BF10 is 13.93. So that means our data are 13 times, almost 14 times more likely under H1 than they are H0. And so from this, I can write some things up. So let's do that. Let's do that, and then we'll come back and play with this output just a little bit to see what all can change if you want to do slightly different analyses. So I'm going to pop back over to my tablet, and let's talk about how to report these results. So the first thing that I would recommend reporting is just to simply report the results of the hypothesis test. So what that means is we want to define the two hypotheses and then specify the prior. Okay, don't just jump in and say the Bayes factor. You need to tell the reader, okay, here's specifically what the hypotheses are, and here's what the prior was that I used. So I might say something like this. Under the null hypothesis, we expect a correlation of 0 between math anxiety and performance. Thus, we define H0 to be rho equals 0. So nice concrete definition of the null. The alternative hypothesis is two-sided, and we're going to call that H1 equals rho not equal to 0. And to specify the prior, we're going to say we assigned a uniform prior probability to all values of rho between -1 and +1. So this little bit of narrative sets the reader up to understand what is going on with this test. Remember, this is the first thing you do before collecting the data. Now, I do want to mention, if you had a one-sided hypothesis test, what would happen then? We'll go back and do that in just a second to see the difference in the output. The next step then is to report your data, or to report, to report what happened after you collected your data. So that's going to be in the form of a Bayes factor. So we'll say we found a Bayes factor of BF10 equals 13.93. Don't stop there. Now tell the reader what that means. Which means that the observed data are approximately 14 times more likely under H1 than H0. This result indicates strong evidence in favor of H1, and I use that label strong from the Jeffreys table that I presented earlier. Okay, so that's sort of minimal. This is like the least amount of stuff that you would want to report. But there's some extra stuff that we can report, and let's just do that. I say this is optional. I really like to do this. Not as many papers do this, and it's not reported in JASP, but you can calculate it, and that is to calculate and report the posterior model probability for your preferred model. So remember from earlier, we can compute that probability by taking the Bayes factor over the Bayes factor plus 1. So in this case, that gives us a posterior model probability of 0.93. So we can report that as follows. Assuming prior odds of 1-to-1 for H1 and H0, our observed data updated these odds to 13.93 to 1 in favor of H1. This is equivalent to a posterior model probability of 0.93. Okay, so that means there's a 93% probability that the alternative is the correct model. Then we can report the results. So that's just the hypothesis test. The next thing to do would be to report the results of the parameter estimation. That is the credible interval. Now I want to point out, this only makes sense if the alternative is the preferred model. If the null is the winner, then there's no estimation that needs to occur, because the null is that the correlation coefficient is 0. Why estimate something that you already know is 0? So this only makes sense if the alternative is the preferred model. So in this case, what we do is we specify the parameter of interest and we remind the reader of the prior. So we might say something like, of interest is the posterior distribution for rho, the population level correlation between math anxiety and performance. Under H1, rho was assigned a uniform prior over the interval from -1 to +1. And then we report the credible interval. The posterior distribution, that is after observing data, for rho had a median of 0.356 with a central 95% credible interval that ranges from 0.134 to 0.554. Okay, so again, all those numbers came directly from this figure. So that's why I really like doing this prior and posterior plot in JASP. Okay, oops, what did I just do here? And that's all for that. So really, that is your template for reporting one of these basic analyses. And you can do the same thing for t-tests. You can do the same thing for ANOVAs. They all work under the same basic idea of building models, comparing the models, estimating the parameters within the models, and reporting them as such. You have to specify the priors, and then you specify the extent to which those priors change with the Bayes factor. So I mentioned that I would address the issue of what if you were interested in a non-directional hypothesis. So here we said it's two-sided. What if it was directional? What if it was one-sided? So let's go back to JASP, and I'm going to open the dialog back up. You'll note here that there is a section for alternative hypothesis. The default is that it's just correlated. So this is could be positive, could be negative. If instead I expected there to be a positive correlation, then I could do that. I could say correlated positively. Now there's a little bug in JASP right now that I'm not sure what's going on, but all I need to do is go up here and just re-enter the correlation coefficient. And when I do that, I'm going to get a different output. So here we'll note that the Bayes factor is now bigger. Let's see if we can figure out why. The reason why is because when I assign a directional hypothesis, I'm saying that before seeing data, I am certain that the correlation is positive. That is, it's between 0 and 1. So you'll notice here, the prior now only ranges over this. It doesn't range over the entire range. And what happens is this prior now comes up here to being twice as tall on the graph, twice as much probability as it did before, because essentially you're taking something that did span a rectangle over this whole range and you've stacked up this part on top of the right-hand side. So that means that the value of rho equals 0 under the null hypothesis is now twice as tall as it was before. And if you remember from that Savage-Dickey density ratio idea, remember the Bayes factor is the factor by which this decreases down to here. So if before it was around 13 and some change, now it's going to be roughly twice that tall, which is where this Bayes factor of 27.83 comes in. So if we use the directional hypothesis, then we get a Bayes factor that's even bigger. And again, you shouldn't hack the hypotheses to get the Bayes factors to be bigger. You should predict hypotheses based on what your prior state of knowledge was. So I would still recommend using the two-sided test because that was, at least in the scenario that I'm presenting, the knowledge that we had. But in some areas, you certainly would expect a positive correlation or even a negative correlation. So in that case, then specify them appropriately. Just know that it will change the Bayes factor, and that's a little bit of insight into the reason why. What if you don't want a uniform prior? What if you really believe that the correlation is small? It's not going to be out here at -1 to 1. Then you can actually change that. You can change this, what's called the stretched beta prior width. The way that works is if you want to make it more peaked around 0, you just make this smaller. So if I change it to 0.5, then, and let me go back up to correlated. I may have to make some things change here. Hang on. Yeah, I've got to change some things, because I want it to get two-sided so you can see the full distribution. Okay, it's really chugging along slow today for some reason. There we go. Okay, now let me actually put the data in, which was 0.34. Gosh, I hope it was 0.34. No, it's 0.37. Hang on. 0.37, there we go. Want to actually have the same data before I start comparing Bayes factors. Okay, here we go. So again, if I didn't want a uniform prior probability, I might instead want something like this, that's peaked at 0 and then sort of slowly goes down to have very little belief that it's at the end here. And in that case, you'll notice my Bayes factor is even higher. It's 18. Again, that's because it's a little taller here than it was. And so now if I am decreasing down to this posterior belief that rho is 0, that's going to be a farther distance. I can make it even more normal distribution-like by making this even smaller, maybe to 0.1. So we'll see what that does to things, right? And so this gives me a Bayes factor that turns out to not be quite as big as you would expect. That's because the posterior gets adjusted a bit as well. But it's still really good evidence that we have a non-zero correlation. And you can also go the other way. If you take your prior width like to 1.5, it's actually going to make it a little taller on the ends, which there might be reasons to believe that that's the appropriate prior. So you can change the prior, but again, I only recommend doing this if you A, know what you're doing, and B, really have reason to believe what the values of the correlation are based on past studies. Okay, so just know that in JASP you can do it. And I'll mention that everything that I'm doing in here is available in JASP when you have your own data file. You don't have to do it through this summary statistics module. Okay, so that's all that. I want to finish up here by going back to the slides and give you some more resources. So maybe you're hooked, maybe you have a place to start. What are the other resources? I'll present two to you that I think are really decent places to get started. One is a paper that just came out last year. I think I've actually got the date wrong on this. this Johnny Van Dorn's article, it was a preprint in 2019. It's actually going to be published probably this year in Psychonomic Bulletin Review. It's already up there. It just hasn't been assigned to an issue yet, I don't believe. But yeah, you can find that with the Google search, or you can aim your device at that QR code, and that'll take you directly to that paper. So these are the JASP guidelines for conducting and reporting a Bayesian analysis. It'll be slightly different than what you've seen today, but it should remind you of some things. And there's also a paper that I'm lead author on with Alexander Lai and E.J. Wagenmakers. This came out at the end of last year in the Journal of Numerical Cognition. And again, it's another tutorial paper using JASP. This one is specifically in my research field, which is numerical cognition, but we walk through a t-test, a linear regression, and a factorial analysis of variance. So again, point your device at that QR code, and you can get that paper. Both of these, again, I think are really readable tutorials to learn more about Bayes. And of course, before you go and stop watching the video, I want to make sure and give a couple of shameless plugs. One is I have a free statistics textbook with Danny Navarro and David Foxcroft, and it's called Learning Statistics with JASP. Not much Bayes stuff in there, but it's a good textbook, I think, for your first year stats courses, particularly in psychology, but also in other disciplines. Again, point yourself toward that QR code, and you can get that book for free. It is a free PDF download. And if you are interested in calculating Bayes factors with analysis of variance summaries, so you have some ANOVA work that you want to get a calculator for, you can't do that in JASP, unfortunately, but you can do it with this little Bayes factor calculator. You put in the F-score and the degrees of freedom, and it's going to pop out stuff very similar to what the JASP screens give you. And again, point your device to that QR code, and you can find that calculator. And I also have a paper in Advances in Methods and Practices in the Psychological Sciences that describes this paper. You can find that linked probably somewhere in that little page. So that's it. What are the take-home points? I'm going to give you three. One, Bayes is really easy. Don't let anybody tell you different. And especially if you have the right software, there's no reason you can't get started with it. Maybe the hard part comes in interpreting, but that's where if you just contact people you know that know this stuff, they can walk you right through it. Yeah, I'm certainly one of those people. Bayes, I think, answers the questions that you thought you were asking. So what you thought you were asking and answering with p-values, you actually can answer with Bayes factors. And then there's always debate in our discipline about should you do testing or estimation, this whole new statistics movement versus the classical null hypothesis testing. Well, I don't think it has to be opposition. With Bayes, you actually get both. Remember in our example, we got not only the model comparison, but also the estimation after the model comparison. So there's no reason to choose because Bayes is very unified and does both for you. So at this point in my workshops, I always spend the last little bit just having conversations with people. Sorry I can't do that this time, but you are welcome to contact me, and I would love to come give a workshop at your university when we can travel again. So certainly send me an email. It's just falconberry@tarleton.edu. And as I said before, I am on Twitter at Tom Falconberry, and then my website is tomfalconberry.github.io. I appreciate the opportunity to share Bayesian inference with you, and I hope that you will contact me soon so that we can have some more discussions and get to do some neat things with Bayesian statistics. Enjoy the rest of your conference, and I hope to see you soon.